If you're an RF professional, you know the space right up against an antenna is a totally different world from the space a mile away. But what's really going on in that chaotic zone right at the source? Well, every antenna creates two very distinct radiation zones, and getting your head around them is, frankly, fundamental to everything we do. So today, let's break down the near field versus the far field. Now, before we dive in, just a quick heads up. This is part 10 of a 20-part series we're doing. All this great info is drawn from a really detailed report on RF propagation by the RFI detectives who are part of Virtualization Options LLC. So if you've been with us for the ride, today's topic is going to build perfectly on everything we've covered so far. All right, here's our roadmap. We're going to start right at the very beginning, the source of the radiation. Then we'll move into that complex and kind of wild near field. After that, we'll see how it compares to the nice, predictable far field. We'll even pin down exactly where that boundary is, and then wrap it all up with why this whole distinction is just absolutely critical for your day-to-day work. Okay, let's kick things off with the source of radiation. To really get a grip on the near and far fields, you have to go back to square one. So let's ask the most basic question of all. Where does an electromagnetic wave actually come from? You know, it's really a beautiful three-step process. First, you have a static charge just sitting there. That creates a static electric field, the E field. Simple enough. Now get that charge moving at a steady pace. Think of a DC current. That creates a magnetic field, the H field. But here's the key. The real magic ingredient to create a wave that actually leaves the antenna and goes somewhere is acceleration. You have to accelerate that charge. That's what creates a self-propagating electromagnetic wave. So now that we know how a wave is born, let's look at the area immediately surrounding that antenna. This place is not simple. It's a complex, reactive zone where the rules you think you know don't really apply yet. So what you've got to remember is that in the near field, the E and H fields haven't locked together yet to form that unified traveling wave. I like to think of it like the turbulent water right behind a boat's propeller. There's a ton of energy churning around, getting stored in the fields, and then whoosh, it just gets returned right back to the antenna on each cycle. It's not actually radiating away efficiently. And what's really fascinating is that the type of antenna you're using completely shapes this near field. For example, a source with high voltage and low current, like a dipole, creates a dominant E field with a super high impedance. But on the other hand, if you have a high current, low voltage source, like a loop antenna, you get a dominant H field with a really low impedance. The whole character of the near field completely depends on the source. And this quote just nails the physics behind it all. The great Heinrich Hertz figured this out way back in 1893. He realized that close to the antenna, the E and H fields are 90 degrees out of phase. And that phase shift, that is why we call the energy reactive. It's like trying to push someone on a swing, but your timing is completely off. You're just storing and returning energy, not actually adding to its forward momentum. All right, let's move away from that chaotic reactive zone. As we get farther from the antenna, things start to calm down. They get much more orderly, much more predictable. Welcome to the far field, where the true radiating wave finally takes charge. As you move away from the antenna, that 90-degree phase shift just collapses. The E and H fields finally lock into a stable in-phase relationship. They become perfectly perpendicular to each other, and both are perpendicular to the direction the wave is traveling. That turbulent water behind the propeller has now organized itself into a smooth, predictable wake traveling across the lake. And this image shows it perfectly. Right at the source, the wave is an expanding sphere. But once you get far enough away, that sphere is so huge that any small piece of it looks and acts just like a flat, uniform plane wave. And that idea of a local plane wave is absolutely crucial for making accurate measurements. And in this far field, there's one magic number that governs the relationship between the E and H fields, 377 ohms. This is what we call the intrinsic impedance of free space. It's the fixed, constant ratio of the electric field strength to the magnetic field strength. The fact that E divided by H is always 377 ohms out here tells us the wave is finally stable and is efficiently carrying energy away from the antenna forever. Okay, this is all great, but let's get down to brass tacks. As an engineer, you're probably asking, so where's the line? Where does that messy near field end and the predictable far field begin? Well, the officially accepted boundary is called the Fraunhofer distance, and thankfully, there's a pretty straightforward formula for it. 2 times d squared divided by lambda.
Here, d is just the antenna's largest physical dimension, and of course, lambda is the wavelength of your signal. So you can see the boundary isn't fixed. It depends on both the size of your antenna and the frequency you're using.
Let's put some real numbers on this to make it concrete. Check out these examples all at 5.5 gigahertz. For a pretty compact horn antenna, the far field kicks in at about 2 meters. But look at that bigger 24 dBi dish. You've got to get all the way out to 6 meters before you're in that stable region. You can see right away how critical this is if you're, say, setting up an antenna test range.
So let's just put it all side by side to really hammer it home. It's night and day, right? In the near field, your fields are out of phase, impedance is all over the place, and the energy is just stored. But get out to the far field and everything's in phase, your impedance is a rock-solid 377 ohms, and that energy is truly radiated. It's a perfect contrast.
Okay, we've clearly defined these two completely different regions. Let's bring it all home. Why is this one of the most important concepts you need to have locked in your brain for real-world applications? Here's the bottom line. For antenna testing, if you try to measure gain or patterns in the near field, your results are gonna be garbage, period. Chasing down EMC and interference issues, that unwanted coupling you're seeing is very often a near-field problem. RF safety. Assessing human exposure is way more complicated in the near field. And for anyone collocating antennas on a tower, you absolutely have to know where those near-field boundaries are so you don't have them messing with each other. This isn't just theory, it's about getting the job done right. So, we've established that out in the far field, we finally have this stable, predictable wave. Which of course leads us to the next big question. Now that we know what this wave is, how does its strength and its shape change as we move around the antenna? And that, my friends, is the perfect setup for our next explainer, antenna patterns.